There is good. So here's a slightly different form of the action. Here's the Lagrange multiplier Z, if you look in the upper left, multiplying the conservation laws for P. Then I have conservation laws I call R. And this is in the version of the theory where we're starting to introduce curved space-time. So let me just ask you to ignore those and ignore the conservation laws multiplied by the script ends are the energy momentum relations, relativistic energy momentum relations for the energy momentum on each causal link. So basically we look at the equations of motion, and when we look at the equations of motion, we notice this equation at the bottom left, that the difference between the Lagrange multipliers for two events that are connected by a causal link, Zi and Zk, connected by the causal link Ki, have a momentum pki, and the equations of motion of stationary phase tells us that the difference between those Lagrange multipliers is proportional to the momentum times some Lagrange multiplier that is some arbitrary scalar quantity for each link. And so that is telling you that the two events in this emergent Minkowski space labeled by the Lagrange multipliers are separated by a space-time interval related to the momentum transfer from one event to the other. And if I have a lot of different relations like that for all the different pairs which are connected by causal relations, and I can consistently satisfy them, then I will reconstruct Minkowski space-time. So that's the idea and outline. And that's just another picture of it that is making it consistently. We have equations of motion for the two causal edges, and by satisfying them simultaneously, we get space-time distances between the events. And this is a theory of relativistic massless degrees of freedom. So we end up with the energy momentum being null and the intervals between the events being null. And this is just reminding us that if we want the inverse momenta, which are given by which are what the Lagrange multipliers that are expressed, and if we want them to look like a position, we have to introduce an arbitrary constant, and that's where h bar comes from. Okay, now, if you go one step in the expansion past that, you can get long chains of events where energy momentum flows principally in one direction and out another direction. And those look like the trajectories of relativistic particles and satisfy the equations that free relativistic particles satisfy. And if you allow there to be events from time to time where more than two inputs and outputs are important, you get interactions. And they look exactly like the interactions between relativistic particles or among relativistic particles. So we get basically the basic dynamics of relativistic point particles emerging in emergent Minkowski space. Okay, so that's the basics. And I think I refer to the papers. Okay, so I'm almost done. The adjacent possible is a nice expression that we get from Stu Kaufman. It means what's the next thing that can be done. So this build the special relativistic version that I mentioned at the beginning. We're using these ideas based on celestial spheres, which various people have been studying as a tool for that. Incorporating general relativity by giving connection degrees of freedom on the causal links. Trying to derive quantum field theory and to distinguish that from relativistic quantum physics. There's a lot of challenging issues there. There's a whole research subject from about 10 years ago called relative locality. We were interested in what happened to basically the phenomenology of dynamical particles when nanospace was curved or otherwise distorted. And and we can develop more of these dual metafields. So that's what the kinds of things we're doing now. And I think that's the talk that's prepared. So thank you very much.